We're going to wrap up this sequence on audio compression, talking about some other techniques, including LPC, physical models, analysis synthesis, and music notation and MIDI. The first of these is linear predictive coding. LPC is often used for voice representation and compression. Here, the voice is regarded as a source plus filter. We know that in speech, pitch and filter coefficients change relatively slowly. They represent muscle movement of a single speaker, and so there are limits to the data rate there. And the compression that you can achieve with LPC is, depending on what you want to compare to, you get down to 1 to 2 kilobits per second, according to one author, typically 2,400 to 7,200 bits per second, reported by Rabiner and Schaefer. And this is another example of intersample redundancy. Here we have a kind of an object model that's used to estimate samples, the object being the voice and the vocal apparatus. Here's what linear predictive coding systems look like in practice. On the analysis side, we take input, we do LPC analysis, which we've talked about before, and we take the residual that comes out of that. Remember, LPC is just estimating a filter. The residual can be analyzed further, and the results of all of this are, first of all, the LPC filter coefficients are used to create a vocal tract filter, which changes from analysis frame to analysis frame. And the residual is used to control a voiced source and a noise source. So the voiced source would be some kind of pulse generator, and we would parameterize it with amplitude, frequency, and perhaps other information. The noise source would be parameterized by amplitude, and the model selects either the voice or the noise source, puts it through the vocal filter to produce output. It is thought by some that physical models and speech synthesis are the future of speech compression technology. Again, the muscles are controlling speech, and they have pretty low bandwidth. So the idea of physical models or speech synthesis is that if you understand these muscles and you understand what the muscles are controlling, then you don't really have to encode the very rapidly varying sound. You just need to encode the control information. Speech sounds are highly constrained, so it lends itself to this idea. In very advanced systems, you may need a one-time transmission of parameters that characterize the speaker. This is not how current speech technology works, but it's a possibility for the future. And we can think about similar ideas for music encoding as well. In music, we have various representations, including music notation and performance information, which are typically much more compact than audio representations. Music notation as you know, something like this, notes and symbols on a page, is a very compact representation, but it does not capture performance information, and expressive performance of notated music is not fully automated, nor are instruments and sound synthesis automated to the point where we could think about actually somehow encoding audio using music notation. Similarly, performance information is a reduction of audio because it encodes not the symbols or the notes of music, but the control gestures of a performer. So, for example, if I'm performing at a keyboard, the exact time at which the key goes down, the time when it's released, the velocity, when I'm stepping on the sustain pedal, what I might be doing with volume controls and other continuous parameters, can all be encoded as performance information and then synthesized later. The standard way to encode performance information is called MIDI. It's an industry standard. MIDI bandwidth is maximum over the standard MIDI communication channel of 3 kilobytes per second, or about 180 kilobytes per minute. That's a pretty low rate, but even then, much more typical is about 3 kilobytes per minute or 180 kilobytes per hour. That's because performers are not maxing out the MIDI channel, and the channel only encodes events when they happen. So, for example, the complete works of Scott Joplin, the famous American composer of ragtime and other beautiful music, his complete works is about 1 megabyte. The output of 50 composers, maybe 400 days of music, could fit into 500 megabytes of MIDI, which is less than 1 CD-ROM worth. So MIDI is a very compact representation, but of course, synthesis of acoustic instruments from MIDI is a problem. To summarize, we've looked at 3 kinds of redundancy in data compression in general. These are coding redundancy, intersample redundancy, and psychoperceptual redundancy. We saw examples of mu-law, ADPCM, and so on, which are simple and fast, but not high quality or high compression ratios. MP3, which we spent a lot of time on, and related schemes rely on psychoperceptual redundancy. These are general purpose compression techniques for audio, especially useful for music audio. They can result in high quality, high compression, pushing 10 to 1 or even better. And they require fairly high computation. But these days, that's not such a problem. And finally, we looked at analysis to construct models and to resynthesize from control descriptions. These are special purpose techniques. For example, the model could be a speech model or a musical instrument model, not really applicable to general audio, but potentially very high quality and very high compression. And this is a research area that's still being pursued.